Okay, now I'll share a document and then we'll start. All right, so last time we looked at Euler's equations of motion for an ideal fluid. We wrote it in vector form. Rho dv dt is rho g minus grad p. So this is a form that you must have seen in your second year course. Now in the previous class, we looked at the form of these equations. The first thing we did was we introduced a modified pressure or piezometric pressure, which is defined as P minus rho g dot r. So if you look at this expression and say there's a function P star, which is the function P minus rho times this function g dot r, which is gxx plus gyy plus gzz, then you can show that grad of P, this being a linear operator, is grad P. Grad of P star is grad P minus, there will be two terms from this product, rho and g dot r. One is rho g and other is grad rho into g dot r. And if the density is constant, then grad rho is 0, so you have only two terms. So using this relation, we can get rid of one term in the equation. So there were two terms on the right hand side. One is the body force per unit volume, other is the pressure force per unit volume. When the density is constant, these two can be combined into this term, and this term can be combined into grad of P star. Okay. Now we looked at Euler's equations of motion along a streamline. This I will upload. So far I have uploaded 8 files. This is the 9th one. I'll upload it today. We looked at different bases other than the Cartesian basis Ex, Ey, Ez. So we took a unit vector Es tangent to a streamline, a unit vector En normal to a streamline, and another vector which is normal to Es, and it is perpendicular to the plane formed by Es and En. So this En we call the principal normal. It points towards the center of curvature. And Eb we call the binormal. And they form another orthonormal basis. So we can write the grad operator as shown here. And we have gone through all this. I just want to give you the final form. You have the S momentum equation along the streamline, the N momentum equation along the principal normal, and the B momentum equation. And when the flow is steady, you see the left hand side of the last equation is 0. So there is no change of the piezometric pressure in the direction of the binormal vector. In the normal direction, in the direction of the principal normal, the pressure gradient is balanced by the centripetal force, centripetal acceleration term on the left hand side. If I move it to the other side, it will become centrifugal force. And you have the tangential acceleration coming into the tangential momentum equation or the S momentum equation along the streamline. Now what we did last time was we integrated this equation along a streamline. So we took the momentum equation in the direction of Es. So if I want to show Es, it is this direction. Okay. So we looked at the component of the vector momentum equation in the direction of Es and integrated it along the streamline. And we came up with this result that the Bernoulli function B, which is P minus rho g dot r plus half rho v dot v. So sum of pressure, potential energy per unit volume, and kinetic energy per unit volume is a constant along a streamline. So we got this result from momentum balance. Now in this course we are dealing with hydraulic machines, and we would like to look at energy transfer. So I'll look at an alternative way of deriving this equation, which will give you some physical insight. So we'll derive today an equation which represents balance of mechanical energy, and we'll do it for the case of an ideal fluid, that is a fluid with zero viscosity and constant density. So we start with the vector momentum equation, which I've written using the piezometric pressure. So I have already assumed that the density is constant, and of course the gravitational acceleration is also constant. We take the scalar product of this vector equation with the velocity vector. So we have rho v dot dv dt is equal to minus v dot grad v. Now instead of taking the scalar product with v, if you had taken the scalar product with displacement vector dr, an infinitesimal displacement, you would have got the work done. Now if you take the scalar product with v, you get the power, because v is dr dt. So it is the rate at which work is being done. Now I had given you an exercise, and it's not difficult to show that v dot dv dt is ddt of v dot v by 2. So this material derivative acts like any other derivative. So twice of v dot dv dt would have been simply ddt of v dot v. And if I look at v dot grad p star, if I add and subtract del p del t, we recognize that I can write it as dp dt, the material derivative, minus del p del t. So this helps us to put the equation which we got over here in a neat form. So v dot ddt of v, we can write as rho ddt of v dot v by 2. The right hand side we'll write as del del t of p star minus ddt of p star. So the second term is the material derivative, and the first term is the Eulerian derivative, temporal derivative, whatever you call it. The reason we are doing it is that the ddt we have seen is a linear operator, so we can move this term to the left hand side and combining it with this. And rho being a constant, I can move it inside the derivative. So we can write this equation as the material derivative of the sum p star plus half rho v dot v equal to del del t of p star. Now we can rewrite this equation using the static pressure or absolute pressure instead of the piezometric pressure. So we use the relation that p star is p minus rho g dot r. So what we have got from this mechanical energy balance is that the material derivative of the sum of pressure, potential energy per unit volume, and kinetic energy per unit volume is this unsteady term, the derivative of the piezometric pressure with respect to time at a given point. So you will recognize p minus rho g dot r plus half rho v dot v as what we were earlier calling the Bernoulli function. So it's a function of x, y, z, and t, which is p of x, y, z, and t minus the constant rho into g dot r, which will depend on x, y, z, and half rho into v dot v, and here v also depends on x, y, z. So we have the material derivative of the Bernoulli function equal to del del t of p star. Now this material derivative I can write as the Eulerian derivative del del t plus the convective term v dot grad v. Okay. And v, as we have done last time, we can write as this magnitude v, capital V, into the unit vector es, which is in the direction of the velocity vector v, and incidentally that is also a unit vector which is tangent to the streamline. And es dot p we can write as the directional derivative del del s. Okay, so we get del B del T plus V del B del S equal to del T of P star. Now we look at the special case when the flow is steady. So what does steady flow mean? Anyone?
Steady flow is unchanged with time. The flow function is not a function of time
At a given point.
at a given.
Okay, that is the key. So del T is the partial derivative. That means it is the rate of change at a given point where x, y, z is fixed. So then del B del T will be 0, and also del T of P star will be 0. So it follows that when the flow is steady, and of course inviscid, and the density is constant, and the gravitational acceleration is constant, this mechanical energy balance reduces to V multiplied by del S of V equal to 0. But when the right hand side is 0, we can drop the V on the left hand side, and it reduces to del V del S equal to 0, which is what we had got from the momentum balance. Okay, so what we see is that the balance of mechanical energy is giving you the same result as the balance of momentum along a streamline for the special case when the flow is steady. So this means that V doesn't change with S, and S is the arc length along a streamline. So that means the numerical value of V will be a constant along a streamline. It could vary from one streamline to the next, unless, as we have argued before, and you have read in your second year course, the flow is also irrotational. But in general, you can have inviscid rotational flows also. So the conclusion is that the balance of mechanical energy for steady inviscid flow of a constant density fluid in a constant gravitational force field is the Bernoulli equation that we have seen. So there are two interpretations of this Bernoulli equation. One is that under certain conditions, it represents momentum balance along a streamline. That means you can get it from the momentum equation. And the other viewpoint is that it represents the balance of mechanical energy along the streamline. Of course, assuming that all these conditions that I've stated before are valid.
Sir?
Yeah.
Sir, what did you say right now about the rotational criteria, about the irrotationality of the flow? Is it necessary for the Bernoulli equation to be valid along a streamline?
No. It is not necessary. If the flow is irrotational, then the value of B is a global constant. It does not vary from one streamline to the next. Okay, if you're interested, then in the next class, I'll show you the reason why it doesn't vary. Okay.
And if there is if the flow is not irrotational, so the curl is not 0, so in that instant, Bernoulli equation will be valid along a streamline.
Yeah, it will be valid only along a streamline. So if you say B1 equal to B2, where 1 and 2 are 2 points, that is valid only along if the 2 points are on the same streamline. If the flow is rotational, but these 4 conditions are satisfied. That is, if you say flow is steady, that means at a point it doesn't change. The flow quantities do not change, but they can vary spatially. And of course, you are neglecting viscous forces. It's inviscid. You're saying density is constant, which is a very good approximation for a liquid. And that is the relevance of it for this course. And G being constant is another very good approximation because the length scales involved are laboratory scale. Okay. So only problem is with this assumption, the flow being inviscid. So when these 4 conditions are satisfied, then we can say that this Bernoulli function at point 1 and point 2 are the same along, provided the 2 points 1 and 2 are on the same streamline. But if I take 2 points on different streamlines, then B1 will not be equal to B2 in general. That is if the flow is rotational. But if you look at the special case when the flow is irrotational, then you can take any 2 points in the flow field and you can apply Bernoulli's equation between them, provided again, of course, the flow is steady, density is constant, and the gravitational acceleration is constant. Now there are various forms of Bernoulli's equation actually. Okay, if the density is varying, but the fluid is what is called a barotropic fluid, you have another form where instead of P upon rho, you will have integral of dP by rho. But let us not worry about it because we are not dealing with compressible flows. Okay, this is not a course on fluid mechanics. I'm just reviewing those aspects of fluid mechanics which are relevant to this course. But then it's a good idea to also tell you what are the other things, related things. Okay. And this important thing is the flow must be steady. Okay.
Sir, why was V dot grad P 0?
No, grad P will not be 0.
No, like we equated V dot grad P along a streamline to be 0, right?
Yes. V dot
Why
grad
so?
P. If you go back here, this quantity, if look at this equation. If I say it's steady, then del T of V is 0. And
Yes.
del T of P star is 0. Then you have V dot grad P is 0. So when V dot grad P is 0, V is a constant along a streamline. If I say, for example, the material derivative of B is 0, then you can say that B is a constant along a path line. Okay. So these are
Yes.
things that we study in the second year. So I'll show you in the next class how B varies with from one streamline to the next. Okay.
Yes, sir.
All right. So what I'll do now is I'll stop sharing
Sir.
this. Yeah.
Can you please once elaborate like what is this balance of mechanical energy?
Okay. Mechanical energy means the sum of pressure, potential energy per unit volume, and kinetic energy per unit volume.
Yes, sir.
It is not intermolecular energy. Okay, internal energy. So when you apply, say, the first law of thermodynamics, it is balance of total energy. So there you have the mechanical energy. Also, in addition, you will have the energy associated with the molecular motion. So this kinetic energy is what you may call bulk kinetic energy. Okay. So then when there is bulk motion of the fluid, you have this term. Now suppose you have a fluid which is at rest. Sorry, there is a disturbance. Should I mute all?
Yes, sir.
Okay, anyway. Yeah, suppose you have a gas at rest. Okay, consider a gas in a cylinder with a piston. There's no bulk motion of the fluid, but the molecules are moving at random with large speeds. Okay, but since they're moving in all possible directions with equal probability, if you take a kind of average, taking into consideration the direction of the velocity, the vector v averaged over several molecules will be 0. But the magnitude of v, which is the speed, that will be very large. That will depend on temperature. Okay. So there is some energy associated with the intermolecular motion. So when you look at the first law of thermodynamics, you talk about internal energy, which is the intermolecular energy. Okay. Now, you have had a course on basic thermodynamics. You have studied heat engines. Okay. Now, the efficiency of a heat engine cannot be 100%. You know that. Okay. Because at least if it wants to continuously extract work, it has to operate in a cyclic process. And in a cyclic process, the heat engine has to exchange energy between two reservoirs. So it will take heat from one reservoir and throw away a lesser amount of heat to the another reservoir at a lower temperature. And the difference of this heat is the work that you extract from the heat engine. But that heat that you reject, that cannot be 0 because that will violate the second law of thermodynamics. Okay. So when you're looking at energy conversion, and Professor Pikadas will be talking about power plants. All right. There you'll see the efficiency cannot reach 100%. Okay. Because converting internal energy to work is not easy. Converting heat to work is not easy. You can convert all of heat to work but only for a short duration. It cannot be a cyclic process. In a cyclic process, heat cannot be completely converted to work. Okay, but these forms of energy, the potential energy, the kinetic energy, and the energy of a constant density fluid which is associated with pressure, they can be completely converted to work. There is no restriction on it from the second law of thermodynamics. Of course, in practice, there will be viscous effects which we have not considered while deriving this equation. Okay, so efficiency will not be 100%. But if you make an idealization and say the fluid is an inviscid fluid or an ideal fluid, that is not a violation of the second law of thermodynamics, although that is impractical. Okay, so these are what you may call high grade energy. Okay, and in thermodynamics you must have studied about loss of available energy. Okay, so whenever the entropy of the universe is increasing or entropy is generated or produced, there is a loss of available work. All right, so the availability here of this mechanical forms of energy is the maximum. We can convert all of it to work in principle. Okay, so by mechanical energy here, this term, here we mean the sum of kinetic energy and potential energy. In some contexts, it is just the sum of kinetic and potential energy. But in the case of a constant density inviscid flow, you can see that you can extract pressure by reducing, you can extract work by reducing the pressure of a fluid. Okay. Now, for example, any other queries, or then I'll open another document. Okay, I'll stop sharing this.
Hello.
Okay, sorry, I got accidentally logged out.
Sir,
Yeah,
I had a doubt. Like
yeah.
when we are talking about like when in a general flow, like if we consider constant potential energy, then when there is pressure reduction, there's increase in velocity and hence kinetic energy, right?
Could you say that again?
Sir, in a flow, like where we consider the potential energy to be fixed and constant.
You want to consider potential flow?
No. Potential energy is not a factor, like it's considered constant.
Yeah, okay. Before that, before I answer your question, then let me show this what I meant. So I've shown you this figure before. Suppose this on the right you have the Pelton turbine. Okay, and you have water at the top of a mountain or hill. Okay, so you have one reservoir which you call the head race, which is at a certain height, and the water from the turbine will fall below into another reservoir which is called tail race. So this is called tail water, and this is called head water. And this inverted triangle and these three lines, you know, it means that the pressure here is atmospheric pressure. So you have air above and you have air on this side. Okay. Now, what will happen is, of course, there will be valves in the system. the water will flow from the head race, the upstream reservoir, through what you may call a pressure tunnel or pressure pipe. This is a shallow pipe which goes to a point which is directly above the turbine almost. And then it will fall down vertically, almost vertically, through a pipe of large diameter which is called penstock. Okay. Now consider fluid particle somewhere here. Okay. Its velocity is 0, so there is no kinetic energy. And the pressure is atmospheric pressure. But if you consider the datum to be this level, the level of the center line of the nozzle, okay, from which the water is directed to the hydraulic turbine, okay, and then the height of this free surface of the water in the head race is what I'm calling the gross height, HGR, or I'm using a symbol simply H1. So the potential energy here is the density of water, potential energy per unit volume is rho times G times H1. Now when the fluid particle moves along a streamlined steady flow through this pipe, okay, and it goes down, what happens? The potential energy will reduce, and what will happen to that energy? It will be converted to kinetic energy. Okay. So the fluid at this point here, inlet to the nozzle, will have very high kinetic energy. And when it goes to the nozzle, it is a converging passage. If the density is constant as the fluid particle moves along through this nozzle, due to the reduction in area, the velocity will increase. So there's a further increase in the kinetic energy. So the fluid which is coming out here of the nozzle has high kinetic energy. And when it impinges on the bucket here, it causes a rotation. What happens is you're transferring this kinetic energy of the fluid to the mechanical energy of the shaft or rotor. And on that shaft, an electric generator will be mounted. So the mechanical energy of the shaft will be converted to electrical energy. So this is the energy conversion. So you see here, it is the potential energy of the fluid which is first converted to kinetic energy. Now, when the fluid is coming out, the liquid is coming out of the nozzle, what is the pressure here? It is surrounded by air on all sides. So pressure is atmospheric pressure. Okay. So between the inlet, if you take a streamline from the free surface of the head race through the pipe down over here, okay, then you see that there's no change in the pressure between this point and the outlet of the nozzle, because both are atmospheric pressure. So what has changed? Well, there has been a conversion of potential energy to kinetic energy. Okay, now I can go back and answer the query that you had.
Yes, sir. So what I was talking about is, let us take a flow in which like the potential energy is fixed and constant of the flow. Hello.
Potential energy, of course, above a certain datum.
Yeah, so we fix that level above datum, so potential energy is constant. And then what we do is like, for example, we take a nozzle there. So the pressure will decrease and the velocity of the fluid will increase, right?
Right.
And which means that the kinetic energy of the fluid is increasing as it's passing through the nozzle.
Right. So if you look at this nozzle, it is horizontal. So if you go along this red line over here, as the particle moves from this point where I place the cursor to the outlet, the change in potential energy is 0 because it's horizontal. There is a change in pressure and there is a change in kinetic energy. So the decrease in the pressure is equal to the increase in the kinetic energy if you neglect viscous effects.
Yes, sir. So which means that the kinetic energy is increasing.
Right.
So by energy conservation, does it mean that the internal energy of the fluid should decrease?
No, if there is a viscous effect, then some of the mechanical energy will be converted to internal energy of the fluid. So that is what you call loss of head.
No, but let us ignore viscosity. Let us consider inviscid flow. Then in that case, as the kinetic energy of the flow is increasing,
Right, right.
Does it mean that the internal energy of the fluid must decrease as the kinetic energy is
The
increasing?
pressure is decreasing. Yeah. So if we
So-
consider there will be a pressure drop across the nozzle. So if you look at the inlet of the nozzle and the outlet of the nozzle, there will be a change in pressure. So let me put it this way. When you apply Bernoulli's equation, instead of saying V is constant, let us say there are 2 points, 1 and 2, on a streamline. And that streamline also happens to be a path line because the flow is steady. So when the fluid particle is moving from an upstream point 1 to a downstream point 2, the sum of pressure, kinetic energy per unit volume, and potential energy per unit volume is conserved. It has the same value, making all those assumptions. So that means if you look at the sum of 3 terms, the change in pressure plus the change in potential energy plus the change in kinetic energy, that is equal to 0. So you should look at the change in the quantities. When
Yes,
you
sir.
move from
So
one point to the next.
what we are saying is that the flow work is equal to the increase in kinetic energy, right?
You're talking about a case where the change in potential energy is negligible, right?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
In that case, the change in pressure plus change in kinetic energy must be 0. That means if the kinetic energy increases, the pressure must decrease. And if the kinetic energy decreases, the pressure will increase. When you look at the change, it's an algebraic, it has an algebraic sign. It can be plus or minus.
Yes, sir, of course. So that is done. Yeah. So what we are saying is, so the change in pressure term reflects the flow work, right?
If you combine the pressure and the gravity, then it's the change in piezometric pressure plus the change in kinetic energy, which is 0.
Yes.
That's
Sir.
another way of putting it.
Yes, sir. Yes, sir.
Change in piezometric pressure plus the change in kinetic energy is 0. Or change in the static pressure plus change in the potential energy per unit volume plus the change in the kinetic energy per unit volume is 0. So sum of these 3 forms of energy, actually pressure is not an energy, but P divided by rho is a form of energy when the density is constant.
So P divided by rho is a form of energy which is related to flow work, right?
You can call it flow work. Okay.
So that flow work will have a source from which
No.
that source would be doing the work, and then
it also applies to compressible flows. Okay. All right. What I'll do is next time I'll talk about it. Do you know what is a conservative force field?
yes, sir.
Yes,
It means
sir.
the work done is independent of the path. The work done is independent of the path.
Yes, sir. Yes, sir. Yes, sir.
Okay, that means if you go from one point to another, say 1 to 2, and you come back from 2 to 1 by along another path, the cyclic integral of f dot dr will be 0. Okay.
Yes, sir.
It's possible if you can write as grad of some scalar potential.
Yes, sir.
Okay.
Yes, sir.
So we can show that when the density is constant, you can write the Euler equation as grad of P upon rho. Okay. So since you are interested, I'll show it to you in the next class.
Yes, sir.
Okay. Why pressure? P upon rho, it has the units of pressure. P upon rho has the units of work per unit volume.
Yes, sir.
Because pressure is Newton per meter square, divided by rho, that is kg per meter cubed. Okay. And you write Newton as kg meter per second square, then you'll see that it will have units of meter per second whole square. Okay. Meter per second whole square is joule per kg.
Yes, sir.
Okay. So it has the units of work per unit volume. Okay.
Yes, sir.
But unless the density is constant, you cannot interpret P upon rho as a pressure energy. Okay. So if you look at undergraduate books on fluid mechanics, some authors make a statement that you should not call it pressure energy. So that is true because pressure itself is not energy. But we can show rigorously that if density is constant, then the P by rho is like a potential energy. Just as you have gravitational potential energy. Okay. Likewise, you will have, so G dot R or GZ, let us say, if Z is a vertical coordinate. What are the units of GZ? It is meter per second square into meter. So that is meter per second whole square. Okay.
Yes.
So P upon rho also, we can write the force as a conservative force field rad of P upon rho, but only when the density is constant. Okay.
Yes, sir.
So we can interpret it also as a kind of energy. Okay. Or to be more precise, then I should go back to the model equation and divide the whole equation by rho and then explain it that way.
Yes, sir.
Okay. But anyway, what I wanted to explain the physical concepts that in the case of hydroelectric power generation, and this figure is a schematic of that, what you're doing is you're converting the potential energy of water at the top of a mountain or hill to kinetic energy of water. And when it impinges on the bucket, from the inlet of the bucket to the outlet of the bucket, the pressure doesn't change because it is exposed to the atmosphere. So you're not changing the pressure of the fluid. What you're doing is you'll be reducing the kinetic energy of the fluid, and that reduction in the kinetic energy of the fluid as it moves from the inlet of the bucket to the outlet, that will be reflected in the energy of the rotor, which will start rotating. Okay.
Yes, sir.
So this is what is called a pure impulse turbine. In a reaction turbine, part of pressure is also converted to work, so you get more work. Okay. So in this case, you're not able to convert, tap the pressure and extract work from the pressure. You just tap the kinetic energy and extract work from the kinetic energy. But how did you get the kinetic energy? You got it from the potential energy. Okay. So that is why you need water at the top of a hill or a mountain if you have a hydroelectric power plant, or even a dam. Okay, a dam will have a large height. So the water on one side of the dam will be at a higher elevation, and the turbine will be at the bottom of the dam. Okay.
Yes, sir.
All right. So I'll stop sharing this document and open another document. Okay. So we have talked about this Galilean transformation before, but not all aspects of it, and I've added new material to it. Okay. So today I'll try to give you a physical picture, and then we can fill in the mathematical details later on. Okay. So here, as you have seen, as we have discussed before, we have a reference frame on the left, which is stationary. And you can imagine you have an observer A sitting on this frame. And you have a reference frame which is translating. That is the frame on the right. And it's moving with a constant velocity. The magnitude is constant, direction is also constant. And it's moving parallel to this axis. So the distance between OY and O prime Y prime keeps increasing with time. So if there's the initial distance, which I'm calling x subscript I and IT for x initial, then x initial is the initial distance at time t equal to 0, which could be 0. Okay. To that you have to add u times t, which is the distance traveled by this axis O prime Y prime in the direction of the vector Ex. Okay. And this was the coordinate transformation. So we took a coordinate system where y prime is y, z prime is z, and x prime is. So if I have a point P here, what is x prime? It is the coordinate, x coordinate with reference to the frame on the right. So if I drop a perpendicular here, the distance from this foot of the perpendicular here and O prime is what we are calling x prime. And if I take the distance from this point to O in the x direction, that is what you're calling x. And this x and x prime, you can see, differs by the distance between the axis OY and O prime Y prime, which will keep on increasing with time as ut. Okay. So x prime is smaller than x. Okay. Now, using this, you can make several predictions. So what you're assuming is the vector u, which is u times dx, is the velocity of the origin O prime of the coordinate system. And we will assume that this is a constant. So both the frames are inertial frames. And later on, we'll consider a frame attached to the bucket of a Pelton turbine and apply Newton's law using the velocities in that frame. Okay. Now, certain things I've already shown you before, but we need to look at it in more detail later on. For the timing, let me just say that the spatial gradients, the partial derivatives in the two frames are the same. This is easy to show using the chain rule. So the grad operators are identical and the divergence operators are identical. But if you look at the partial derivatives with respect to t, they are not the same. Okay. So del del t is del del t prime minus u del del x prime. Okay. So first, let me talk about the physical meaning, then we'll talk about the mathematics. So this temporal derivative del del t, or the Eulerian derivative, physically it means the time rate of change of this flow quantity p at a point xyz which is fixed in the stationary frame of reference. And the other derivative, which I'm calling del del t prime, is the time rate of change of p at a point x prime y prime z prime which is fixed in the translating frame of reference. But a point which is fixed in the translating frame of reference is moving with reference to an observer on the ground who is attached to the stationary frame of reference. So the physical meaning of these two partial derivatives are different. Both of them are the time rate of change at a point, but which point? In one case, it is a point fixed relative to the ground. In the other case, it's a point fixed relative to the moving frame. So let us consider a physical example. Suppose you have an airplane which I've just shown this way. It is moving to the left with a speed which is v0. Okay. And I'm considering here OXYZ, which is a stationary frame of reference on the ground. And you have an observer, I've indicated by this symbol over here. I'm calling the observer A. Now, let us say you have a point P with a position vector RP relative to this coordinate system, which is fixed in this frame. Okay. And let us say the observer A is measuring the velocity at this point P. Okay. Now, what do you think? Will the velocity measured by this observer at point P, will it depend on time or will it be independent of time?
Independent of time.
Okay, let us say this way. Suppose the plane is far away. The atmosphere was at rest. Okay, the air in the atmosphere was at rest. So the velocity at this point will be 0. Okay. Now when the plane is coming this way, this is solid. So it is pushing the fluid which is in front of it, in front of its nose. Okay. So when the airplane nears this point, this is of course an enlarged view, it will set the fluid in the neighborhood, in the vicinity of this into motion. Okay. So suppose the observer A has put a laser Doppler velocimeter focused at this point. You will suddenly see a non-zero velocity because the air in front of this moving plane has been set into motion by the movement of the solid body. Okay. Do you agree with this?
Yes, sir.
So initially the velocity was 0, and when the plane comes near, it will become non-zero. Now the plane will go away towards the left, far away. Okay. Now what will happen to the fluid which has been set into motion? Viscous effects will damp it out. Transients will decay, and again it will eventually come back to 0. Okay. But if you consider the entire period of measurement before the plane came here and the plane went away, there is a variation with time, right?
Yes, sir.
So this del phi del t, the measurement at a point, suppose phi is a velocity component, say Vx, or even pressure. Okay. Okay. When the plane comes, there will be pressure pulses in front of it. Okay. Which will travel. Of course, pressure pulses will travel with the speed of sound. So this del t, if it is zero, we call it steady. If it is non-zero, we say it is unsteady. Okay. So if I ask you, is the flow steady at the point P, which is fixed in the stationary frame of reference? Or in other words, the flow as seen by observer A. Okay. Now, after all this discussion, what will we say?
Not steady.
No, sir.
It is not steady. So the answer is no. Okay. So I summarize these points. When the airplane is far away from point P, the velocity at point P is zero. The motion of the airplane induces a flow in the region close to the moving plane. So as the plane approaches point P, the velocity at point P becomes non-zero. After the plane moves far away from the point P, the velocity at point P eventually, that means after a long period of time, long duration of time, will become zero due to the damping effect of the viscous forces. So the velocity measured by observer A at point P then will vary with time, and hence the flow is unsteady as seen in the stationary frame of reference. Okay. So now if I go back and look at this result, which we'll derive later, this del t of phi here, this will be non-zero. Okay. But we don't know about del t prime of phi. So what is the physical meaning of this? Now consider the same plane, and let us say you have now a coordinate axis I've drawn in red, O prime, X prime, Y prime, Z prime, which is attached to this translating plane. Okay, and I have put another symbol here. A person sitting here whom I'm calling observer B is inside the plane, let us say. Oh. And I have considered a point Q with position vector I'm calling R prime of Q with reference to this. And let us say this point is fixed related to the plane. So as the plane is moving, the point is also moving. Okay. So observer A will see the point Q also moving, because the point Q is fixed relative to this observer. Okay. Now, the observer B will not feel the motion of the plane because he's sitting over here, but he'll see the surrounding fluid which was at rest. So if you look at this figure, you look at the velocity somewhere here. Okay, far away to the left of the plane, the velocity is zero as measured by observer A. Okay, but if you look at the relative velocity relative to the second frame, the fluid will be moving from left to right with the velocity speed, which is the speed of the plane, v naught. We agree with this?
Yes, sir.
So spend some time thinking about it. Okay, so in this figure, the plane is moving from right to left in this direction of this arrow with the speed which I am calling capital V naught, and the surrounding air initially was at rest. So at the left here, far away from the plane, the velocity as measured by observer A will be zero. In fact, even at point P, it will be zero when the plane is far away. Okay. But if you look at observer B, suppose he is hanging out a probe and measuring the velocity at point Q. Okay. So the plane is moving. The observer B is moving along with the plane. The point P, the measurement point, is also moving. So the measurement point is moving. Okay. Moving with reference to the ground frame. Okay. That is as seen by observer A. Okay. But he will always see, observer B will always see the fluid moving from left to right with the speed of the plane in the opposite direction. because this is relative motion. Okay. So now you can have a situation where the flow quantities at point Q as measured by observer B are unchanged with time. Just think about it. Okay. Suppose the point Q is somewhere here. Then the velocity all the time will be V naught. Okay. And it will be from left to right. Okay. So the flow, if I say, flow will be steady relative to the translating frame, but unsteady relative to the ground frame. Does this example make it clear?
Yes, sir.
So you can have a situation where del phi del t prime is 0, that is the flow is steady in the translating frame of reference. If del phi del t prime is non-zero, then the flow is unsteady in the translating frame. Okay. Now go back here to this relation between the two partial derivatives. Okay. The difference is in the first equation minus u del del x prime of phi. So if the flow quantity is varying with the coordinate x, okay, then you can have a situation where the derivative on the left hand side is non-zero and the derivative on the right hand side is 0. Okay. So then del del t of phi will be minus u del del x prime of phi. Okay. And this is the same relation where I've kept the prime quantities on the left hand side, and I've also used the fact that del del x prime is del del x. Okay. So in the second equation, the temporal derivative in the moving frame is on the left, and the sum of temporal derivatives in the ground frame and the spatial derivative in the ground frame is the added together over here. So if the flow is steady in the unsteady in the ground frame, the first term will be non-zero. Okay. But to that, if you add this term, if they have opposite signs, then the sum might be 0 and the flow might be steady in the moving frame. Okay. So you need to think about it. But at least with this physical example, I hope the physical meaning of the partial derivatives is now clear. So you can get the partial derivatives by measuring with time the velocity or pressure at a given point. So the point might be fixed or moving. Okay. So in the first case, the point is fixed relative to the ground frame, but moving relative to the translating frame. And in the second case, the point is fixed relative to the moving frame, and hence it is moving relative to the ground frame. Okay. So the measurement points are different. So if you measure the quantities with time, you can use numerical differentiation to find the derivatives, time derivatives, the rate of change at that point. Okay. And if the quantities change with time, you say it's steady. If it doesn't change with time, you say it is unsteady. Sorry, if it doesn't change with time, it is steady. If it changes with time, it is unsteady. So an unsteady flow can be made steady by changing the reference frame. Okay. So this is a fact that we'll utilize in the analysis of the Pelton turbine. Okay. So what we'll see is that you cannot use Bernoulli's equation with the velocities as measured by observer A because the flow is unsteady. Okay. But you can, I'll show it to you, you can use Bernoulli's equation with the relative velocity because it may be steady as seen by observer B. Okay, it is now 11:55, 56. Okay, so I'll not, I'll stop here and answer any queries. And then we'll meet again tomorrow. Any questions? Okay, then you may have another class. So should I hang up? So as mentioned before, Professor Das has created another MS Teams account, and today he'll take the class at 2 p.m. You might have seen the mail which he sent.
Sir, will we have class tomorrow at 8 a.m. in the morning? The 8 a.m. slot.
That will tell you. Okay. If he
Okay.
wants to take the class, let us see how he feels after taking the class.
Okay.
So he'll tell me and I'll convey to you. Or will you check your mail? Okay.
All right, sir. Yeah.
Yeah. So as scheduled, he was supposed to take the morning class at 9 and the class from 4 to 5, and I was supposed to take the class from 5 to 6. According to the first mail which we had sent to you. Okay. But let us see how he feels after taking one class. So if necessary, I'll take both the classes in the afternoon tomorrow. Okay. He may take one class, or if he doesn't want to take the class in the morning, I may take the class in the morning. We'll inform you.